lot heavier than I thought. Hi, welcome to Beginning Engineers. Today we're going to model probability in real life using lottery tickets. Recently, I bought my brother $210 worth of lottery tickets because I want him to develop a gambling addiction. No, just kidding. I thought it would be fun to actually do something in real life. So this is going to be a little bit different than my usual videos, but don't worry, I'll still have some good PowerPoint slides, but there'll be a lot of actual real life probability. So we're going to model expected value and probability trees in real life. Let's do it. What is expected value? Expected value is the long-run average value of repetitions of the same experiment. Take, for instance, rolling a die. A die with 6 sides. You have 1, 2, 3, 4, 5, and 6. Those total 21, but if you divide that by 6, each possible outcome, you get 3.5. The expected value of rolling a die is 3.5. If you roll a die long enough, you'll see that your results average to be 3.5. The more often you repeat the experiment, the more likely the result will reach this expected value. This is due to something called the law of large numbers, which essentially states the more you repeat an experiment, the closer your average will get to the expected value. This holds true even if the probability of each outcome varies, so not a dice or something where every outcome is just as likely, as long as you weight the values appropriately based on their probability when calculating the average. Let's stick with our dice for an actual example. Assume someone offered you a gambling game that you had to pay $100 to play once. If you rolled a 3, you got $500. But if you rolled anything else, you lost $100. Would you play? In this game, if you rolled anything besides a 3, you paid $100 and win nothing. We'll represent that with negative 100. If you roll a 3, you gain 500, a positive 500. But again, you only have a 1 in 6 chance of rolling that 3. You take your negative 100, your loss of $100, and multiply it by 1 over 6. You add that to itself 5 times because 5 of the 6 outcomes have that same result, but then you also add in the $500 you would win on the 3. It ends up canceling itself out and being $0. And the first one is a loser. You need 3 of something to win. So, after scratching off all of those lottery tickets, what do you get? Well, even by not knowing the probability of winning a certain amount of money, we can still get to an expected value if we play the game enough. You can see on the right-hand side a little bit of my Excel journal of all the winnings. I kept track of what every single ticket was, whether it was $1, so no win, $1, $2, all the way up to $20, our maximum win on a single ticket. I charted out the results of every single ticket and the running average, which would become the expected value. You can see we had some good wins there in the beginning, but then an unlucky streak that actually dragged us down to below what I believe the expected value is, 59 cents. But you can see as the experiment went on and on and on, and we got up to the 210th ticket, we began the trend towards that 59 cents value. And over time, with more observations, that 59-cent value would become harder and harder to change. So if I had done 500 lottery tickets instead, I think you would see that the last 200 or so barely deviated from around 59 cents. So let's use our lottery tickets results to build an expected value equation. The overall odds of winning the game we played are 1 in 4.74, with prizes of 1, 2, 3, 5, 10, 20, 50, 100, and $500. So our expected value that we measured of 59 cents is equal to the $1 times the probability of winning $1, $2 times the probability of winning $2, on and on until you get to $500 and the probability of winning $500. Based on our 210 lottery tickets, we are able to build out a pretty decent version of this formula. But of course, we didn't win anything more than 20, so I'm not really sure what the likelihood of each of those prizes is. And the fact that the probability of winning 20 was more likely than 10, it just meant that we got lucky, and we really needed a larger sample size. You can see at the bottom, I recorded the quantity of each prize we won and what probability that gave for that prize level. Summing up all the probabilities, we got to 20.9% odds of winning, whereas 1 in 4.74 odds equals 21.09%. So our sample size was a pretty good volume. See how close we got to the actual odds? But that is expected value, an overall average. What about the probability of a certain outcome? Playing cards are a good way to model probability paths and how the outcome of a certain event can be calculated by subtracting the odds of it not happening from 1. For example, what would be the odds of randomly drawing a Jack of Hearts from a 52 card deck? Well, there's only one Jack of Hearts, so it would be 1 in 52. But what about the odds of drawing a Jack in general? Well, that would be 4 in 52. So what about the odds of drawing 2 Jacks in a row? Is it 4 in 52 times 4 in 52? Well, no, because you're removing a Jack if you get one the first time. So really, it's 4 in 52 times 3 in 51, because the 52 card deck is now down to 51, and the card you took out was a Jack, so there's only 3 left. So the odds of drawing 2 Jacks in a row is 4 over 52 times 3 over 51, which is 12 over 2,652, or simplified, 1 over 221. Pretty slim odds. What are the odds of not drawing a Jack at all? It's the same idea. There's 48 cards out of 52 that are not Jacks. You draw one out, you're down to 47 out of 51 that are not Jacks. Multiplied, that's 2,256 over 2,652, or 188 over 221. Much better odds than drawing 2 Jacks in a row. Okay, so what are the odds of drawing at least 1 Jack in 2 attempts? You could draw it the first time, or you could draw it the second time. Well, here's where things get a little more complicated. Because you know the odds of getting no Jacks at all is 188 over 221, you could just say the odds of getting 1 or more Jacks is 1 minus 188 over 221, so 33 over 221. But again, that's just the odds that you don't not get any Jacks. So this could be 1 Jack or both Jacks. And also for the 1 Jack, that means the first card could be a Jack or the second card could be a Jack. So any of those combinations added together is 33 over 221. If you want to get more specific and say what are the odds the first one is a Jack but the second one's not, or the first one's not a Jack but the second one is, your equation becomes more advanced, or you can use a tool that is a favorite of mine, a probability tree. Let's look at a basic probability tree for flipping a coin twice. The coin has heads on one side and tails on the other. If you flip a coin twice, what are the possible outcomes? You could have heads then heads then tails then heads, or tails then tails. And of course, with a regular coin, the probability of heads or tails, it's 50-50. Each one is as likely as the other, 50% versus 50%. By drawing the probability tree with associated probabilities, we can see that each outcome has a 0.25 chance of occurring, 0.5 times 0.5. And when I say outcome, I mean the end outcome after flipping the coin twice. Heads heads, heads tails, tails heads, and tails tails. But that's not how questions always work. Sometimes the question is, what is the chance I'll get a single heads? Well, since it doesn't matter if it comes first or second, there are 2 scenarios with 1 heads. You can see them there in the middle. So the odds are the 0.25 plus the 0.25. It's easy to understand the math when there's only 2 outcomes with equal likelihood. But the benefit of a probability tree is that they are super useful in more complex scenarios. So let's go back to our drawing 2 Jacks or 1 Jack scenario from a deck of cards, where there's multiple scenarios where the probability can change. Ignoring the suit of each card, there are really only 13 types of cards you can draw in the deck. That means picking any one of those has a 1 in 13 chance. If the first card you pick is not a jack, then the next card will have a 4 in 51 chance of being a jack. Slightly better than 4 over 52, which is 1 in 13, because you removed one of the non-jack cards. But that means the next card will have a 47 over 51 chance of not being a jack. If you pick a jack the first time, then the odds of picking another are 3 over 51. I didn't want to draw all the lines because it would add too much to this slide, too many branches to our tree, but you can see I've listed every single card between a 2 and an ace, and you see each one has a 1 over 13 chance of getting picked, 0.077. Then at the very top, I modeled this situation where you pick a non-jack, and then you can either pick a jack with 4 over 51 odds, or you can pick another card that's not a jack, 47 over 51 odds. So multiplying those likelihoods out, not picking a jack, then picking a jack has a chance of 0.00603. And because there are 12 possible pathways that can end in that same result, you multiply that by 12, giving you 0.0724. But there is another path where you can end up with a jack or more. There's actually 2. And again, we're trying to model all the pathways, the total probability of getting at least one jack. So you could not get a jack, then get a jack, that's at least one jack. Or you could get a jack your first time and not get a jack, that's at least one jack. Or you could get a jack your first time and your second time. That's also at least one jack. So by adding together the probability of all those paths, remember, not a jack then jack can happen 12 times, a jack then a jack can happen once, and a jack then not a jack can happen once. Adding those 14 paths together, where you get at least a jack, results in 0.14932. And guess what this equals? 33 over 221. So we got to the same answer the equation gave us, but by using a probability tree, you can better examine very specific scenarios. It's a way to map out everything that can happen so that you can answer super specific questions about probability. Otherwise, I find, at least personally, myself getting lost when talking about probabilities like this. So you can imagine, if we knew the probability of each prize on the lottery ticket, you could answer the question, what are the odds you get nothing on the first 6, then win $50? Well, if you had the probability tree, I could give you that exact answer. But in the interest of time, and because we don't actually know the official probabilities of each prize, save that for another time. It's kind of funny when you're sitting there scratching a bunch of these lottery tickets. When you've had 6 or 7 losers in a row, you begin to think things like, oh, I'm bound to win. And of course, a lot of this is just incorrect psychology, not really based on statistics, but there is a little bit of truth in it. So in my example of the probability tree, the odds of continuously losing do get more and more slim. So there is a little bit of truth to, I'm bound to have a winner coming up, believe it or not. Thank you so much for watching this video. I hope you learned a little bit about how probability works in the real life, specifically expected value and probability trees. If you like this video, feel free to subscribe. Have a great day.